learners, it's Crystal here. I'm just here this morning because I wanted to do another code review with you. It's with Kaggle's community competition about earthquakes. And what's really interesting in this code review is that I initially did it in a deep neural network, and I got like I'm not sure, like maybe 30, 31, 32% MSE. But I was looking at somebody else's work, and he was able to score like 14, believe it was an MSE, using random forest. And so I thought, well, let me see if I can improve my score using random forest. And TensorFlow has a decision TFDS has a decision forest library that you have to import because TensorFlow wants you to stick with TensorFlow. So they give you random forest and gradient boosted. So you can use that, which is really interesting. So I tried out random forest, and I think I had 27. I believe it was 27. And then I thought, well, let me see if I can improve my score with gradient boosted. So I tried gradient boosted, and it was 21. And this was a very time consuming competition for me to undertake. So it took me, like all last night and some of this morning to work on this competition. And then before I made the code review, I thought, well, let me see if I can improve my score with gradient boosted. So that's what I did. I've improved my score with gradient boosted. And so that just goes to show that neural networks are not always the best choice. And when you're working on a problem, you have to select several different models and choose several different models and then select the best model. And so in this instance, the deep neural network was not the best choice. It did not give me the best score. And it did take me a long time to do it because the TensorFlow documentation doesn't tell you how to do advanced arguments. It just said, well, use these advanced arguments, but it doesn't give you a sample code on how to use advanced arguments. So I had to put it away. I had to put it away, go take a shower, and then try some more. And I figured out on my own without TensorFlow. So that's why I'm giving you this code review, to show you that I figured all this out on my own without TensorFlow. Because their code, they don't give you all the code examples. I guess they just assume that if you're clever enough to use TensorFlow, you're clever enough to be able to code it without getting very many code examples. So this is the code review that I did, no thanks to TensorFlow. And so the first thing you can see that my best score was 21. So I'm assuming that's MSE. And that was a gradient boosted. And so that's just telling you that the deep neural networks are not always the best choice. So TensorFlow, in addition to having the neural networks, they also have TensorFlow Decision Forest, where you can use a random forest and a gradient boosted. So you need to try those out too before you make your final decision. So I wrote this program on Kaggle's free online Jupyter notebook, and it's stored in the repository, and it's also, I've made it public so anybody can see it. So the problem statement is predict on building safety during an earthquake, because that's always really important. And then what we're going to do is we're going to import the first set of libraries that we're going to need to actually execute this program. So we're going to import NumPy as NP. That's going to create your NumPy arrays and perform numeric computations. We're going to import pandas as PD. That's going to create your data frames and perform data processing. We're going to import OS, which is going to go into the system and work. And then we're going to import matplotlib.pyplot.splt, which is going to visualize the data. And we're going to import Seaborn as SNS, which, again, it visualizes the data statistically. And so after we have imported our libraries, then what we want to do is we want to use OS to go into the operating system and retrieve the files. And we had 3 files being train, test, and sample submission. So you can see the 3 files that were retrieved. And after we have retrieved the files, what we want to do is we want to use pandas to read the files. So we read the files as train, test, and submission. Those files have been converted to data frames. So we check the train data frame. And so this is a train data frame. One thing that I will say is I had a lot of problems with silly things because basically the column names had odd names, and because the column names had odd names, it was difficult for me, and I had to work around that as well. So I had to work around things that ideally I should not have had to work around if the column names had been given proper names that would be suitable to Python. So I can't say if it would have failed if I had used sklearn, but it did fail using TensorFlow, and then I had to use advanced arguments to get it to work. And when we go into the code, I'll show you how I did that. So we describe our train so you can see some of the statistics when we of every column that was a numeric column when we describe train. We check info. So you can see when we check info, you can see all of these columns or features or floats. And then the actual target is max drift MN. Okay, so we check for any null values. We didn't have any null values, so that's good. So we didn't have to do anything about that. We check the test file. The test file is the same as the train file, except for it doesn't have that max drift MM column because the max drift MM column is your target. We don't have any null values in test file, so that's good. So we don't have anything to impute. And now we check our submission. So your submission is going to be index and it's going to be max drift MM. And that's to do with the safety of a building during an earthquake. So now what we're going to do is we're going to analyze train. And if you look over here, it says your submission, your max drift MM is rounded to 2 characters. So that's very interesting. So you have to keep that in mind. So what I had to do was I had to round max drift MM to 2 characters. If I hadn't rounded it to 2 characters, then what would have happened would be that every instance of the label would have been unique, and it would have meant that I would not have been able to make a prediction. So that's why you have to round it to 2 digits to get it to work. And then so we checked max drift MM on this plot, and you can see this is the distribution that it makes. And it's also important to note that it's skewed. It looks to me like it's skewed to the right. Now we do a value counts after we have rounded the max drift mm to 2 digits, and you can see we've got a few instances where the max drift value appeared only once. And so what we're going to want to do is we're going to want to remove all of those rows of data or examples where the max drift appeared only once. So you can see here where we've removed all those rows of data. And so you can see now we've got 1321 rows of data after we have removed all of the instances where it has appeared only once. And then before we removed all of the instances, the examples where it appeared only once, you had 2922. So you can see that it got rid of quite a few rows of data, and it doesn't do any good to try to include rows of data where the example appeared only once, because the model is not going to be able to make a prediction on it because it doesn't have anything else to base it on. So we filtered it out, and now we check it again on displots, SNS displot, and you can see that the distribution looks different because you don't have as many examples anymore. So what I did was I gave you a little box plot. So I'm not that sure about the safety of a building in an earthquake, but I thought, well, let's check the number of floors. So that's obviously going to have something to do with it. And so your X variable is going to be your number of floors, and your Y variable is going to be your max drift MN. And so you can see that like 3 floors and 5 floors are going to be the least safe, but 1 floor is going to be the most safe. So but that's pretty much common sense. If you have only 1 floor, then it's going to be the most safe during an earthquake. And the more floors you have, the more chance that the building is not going to be safe during an earthquake. Now we do check out the floor height again. We check that out on max drift MN, and you can see that the height of the floor is also going to take into account the safety of the building. So a floor that was 3 meters is going to be safer than a floor that is 3.5 or 4 meters. So that's very interesting. So now what we've done is we're going to check it distance to fault kilometers. That's your X variable, and your Y variable is max drift MN. So you can see that it's giving you how dangerous or how unsafe the building is, depending upon the how far away the earthquake is from the building. So that's really interesting. So you would assume that the closer the earthquake is to the building, the least safe it's going to be. That was just an assumption. Now what I've done is I've made a heat map. And so core equals train.core, SNS heat map core. So you can see the heat map here, and you can see that the most of the columns are not very highly correlated. Some of the columns are a little bit correlated. Now, if I really wanted to, I could go through and delete the columns that are really highly correlated, because that might introduce some news into the system, but when it noise into the system. But whenever I did the heat map, I just saw all the orange and I thought, oh, it's not very highly correlated. But you can see this section right here. This is a section of highly correlated columns. So I could, in theory, try to remove some of those redundant columns and see if I can improve the score. I mean, that's one thing that you could do, is remove some of the redundant columns. But I didn't do it. So you can see here, here's your correlation. So you got one correlation that's at 0.87, and you can look and see anything that's got a high correlation. So, I mean, just looking at it really quickly, I saw the one correlation that's 0.87, but I didn't see anything that's above 9. So maybe there's the possibility that it's not very highly correlated. So now that we have analyzed the data set, or the train set, what we're going to do is we're going to split the train set into training and validation sets. And so we're going to use train test split to do that, and we're going to do it a little bit differently. So instead of defining our x and our y variables and splitting it into x and y, we're just going to split the entire data set. So train PD, comma, val PD equals train test split, train, then test size equals 0.1, random state equals 42, and then you check your shape of train PT, val PD, and test. And we use sklearn's train test split to carry out this operation. Now we're getting into TensorFlow, and what we want to do is we want to install TensorFlow Decision Forest. And the reason why we do that is because that is not automatically installed into the Jupyter notebook. So before we can use it, we have to install it. So we've installed it. So now what we're going to do, we're going to say we're going to import our TensorFlow libraries. And you see that one version 2.11. And it's always a good idea to know what version of TensorFlow you're using. And the reason for that is because TensorFlow goes through so many changes that a lot of their code gets deprecated. So now what we're going to do is we're going to take our data sets and we're going to convert them to a TensorFlow data sets. And this is something that I had to study to get it to work. So label equals max drift mm. So train ds equals tfds.keras.pd data frame to tf dataset. And then we're going to use train PD. It says fixed feature names equals false, because the feature names were not well designed feature names to go with Python programming. So fixed feature names has to be false. Label is label, which is max drift mn, and task equals tfds.keras.task.regression. And we did the same thing with val ds. And with test fit ds, we didn't have a label because test ds did not have a label. And so I got the error message about the fixed feature names, and then so I put the fixed feature names in there. But TensorFlow did not give me a lot of help, so I figured this out despite TensorFlow, where I guess they figure if you're clever enough to use TensorFlow, you're clever enough to do all these modifications that need to be carried out. So I did figure out eventually late at night. Now what we're going to have to do is, again, because the feature names were not very well planned out, not very well designed, I had to go into the TensorFlow documentation and find out about advanced arguments. And then I had to do this all myself without TensorFlow's help. All they did was they gave you the advanced arguments, but they didn't give you anything else to do. So argument equals tfdf.keras.advanced arguments. Then you say fail on non-keras compatible feature names equals false. Because if it's true, then it will fail, which is what happens. So you have to set it up for false. And then model equals tfds.keras.gradient boosted trees model. Task equals tfds.keras.task.regression. And advanced arguments equals argument. And I figured that out without the help of TensorFlow. And then so model equals model.fit train ds. So we're training the model. Got lots of warnings. Then we do a summary of the model. So this is your summary, and it's really got lots of information in the summary. Now what we're going to do is we're going to evaluate the model. Model.compile metrics is MSE, and we're going to evaluate the model. And we had an MSE of 18.8, which is really good, and an RMSE of 4.33. So that's really good too. And then we're going to make predictions on the model. So predictions equals model.predict test ds. So you have to use the TensorFlow data frame to do that. Predictions equals np.round underscore predictions decimals equals 2. So you have to round it to 2 digits. Predictions equals predictions.flatten. So you have to flatten it, well, to make it look better. I flattened it to make it look better. And then you have your predictions. Now what we do is we prepare our submission. Submission max drift mm equals predictions. Submission.toCSV is submission CSV. Index equals false. So we're creating a CSV file. Submission equals pd.read CSV, submission.csv. So we're converting that into a data frame, and we've got our submission. So this is what we have actually submitted to Kaggle. And when I submitted it to Kaggle, I think I got a 21, and the best score is like a 14. And I think that I could actually improve the score by manipulating the parameters, like the number of trees and things like that. But that is one thing that you can do to try to improve your score. But I'm not going to do it in this instance. I might think, oh, well, let me see if I can get it to work, and then try to manipulate the parameters to actually get it to work. But it was not that easy because the feature names were not very well planned out. That was a big problem. And if I wanted to, I could remove some columns of data to try to improve the score as well. But what I might do is I might try to manipulate the parameters some more, see if I can improve my score by manipulating the parameters, because the highest score was 14 and I only scored 21. So I'm going to go ahead and conclude this video. I would like to thank you very much for watching my code review. If you like my video, please like, subscribe, and share. Thank you to my subscribers for supporting my channel, and I look forward to making more code reviews for you in the future.